Alright, are we live? Hello, 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 hello. Hello stream, hello world, welcome, howdy, howdy. So, today we're going to take a look at the next question. It says count numbers with unique digits. So this should be interesting to the LeetCode medium. So we'll take a look, see how it goes. I'm a little later today than I normally would be. Reason being I've been doing some research, I guess. Sort of personal things. So here we go. Count numbers with unique digits. Let's see how we do here. So, given a non-negative integer n, count all numbers with unique digits x, where 0 is less than or equal to x is less than or equal to less than 10 raised to the n. Whoa. Whoa, that's a lot of numbers. Wow. Wow. This actually is not such a hard question, because after a certain point you can't have unique digits anymore. By the pigeonhole principle, if you get past, let's see how many digits you have. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. So once you get to 11 digits, and a number with 10 digits, the first one is, I think, 10 raised to the 9th, right? That has 1, 2, 3, 4, 5, 6. Oh, this is some nice zeros there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's 10 digits. So that's once you get past. Now, I would think you could still be unique, right? You could be 9, 8, 7, 6, 5. These numbers are kind of wild here. 3, 2, 1, 0. But once you get past this point, and you actually don't need to go past 10 to the 11th. You don't need to go all the way to 10 to the 11th. Once you get past really this number, anything over this number is not going to be unique. So all the unique numbers with the unique digits are less than or equal to this number. This is the largest one, which still a lot of numbers to go through, but basically we don't need to consider if n is greater than or equal to, if n is greater than or equal to, I guess it would be, what do we say, 10 to the n? So less than 10 to the n. So that would be if it's n is greater than or equal to 11. Oops. Then you have the same, it's a constant time. You can calculate that directly. It'll be the same number every time. So, and hopefully, I'm not sure how my volume is here. I think it's okay. Yeah, it'll be the same number every time. Yeah, I think we're okay with the volume. I think we're okay. So that's kind of neat. So we really only need to take a look at really 11 numbers, n, 0, 1, 2, 3, etc., all the way up to 11. So we can actually calculate all the, n is even less than 8, excuse me. It's not even, doesn't even go that far. So we really don't need to, we can actually compute all of these numbers directly and just print them out. And maybe there's a way to do it efficiently though. So really we could do this by hand in theory. So 10 to the 0 is 1, it's one number. So we'll say f of 0 is 1. We'll call it f. Okay, f of 1 is 10 to the first is 10. So 0 through 9 is all unique. There's 9 of those. 10 squared is 100. Now how many numbers between 1 and 100 have, and it's actually going to be, you call it G of a range, G from some range alpha to beta, or alpha to beta, where you don't include beta. And you could say f of 2 is going to be G of 0 to 10 plus g of 10 to 100, where g of 0 to 10 is exactly equal to f of 1, which is 9, right? This is sort of a recursive definition, or not recursive, it's not really recursive, but excuse me, we can kind of carry over our results. And actually there is a relationship between g of 10 to 100, or f of 2, and f of 1, and g of 0 to 10. Basically there are 9 iterations, reiterations of sort of f of 1, except with one digit chosen, which means that these 9 different positions, these 9 different cases, are going to have 9. These 9 different cases are going to have one duplicated digit in this set of, there's going to be a set of 10 for each, and each set of 10 will have one duplicated digit, so it'll be 10 minus 1 times 9 plus 9, which should give us 99. No, excuse me. 90. Is that right? Does it give us 90? Does that give us 90 for 2? Or am I crazy? 91? That's 91. It's very close. How did we get this wrong? What did we do? We did something wrong here. I'm sorry, f of 1 is 10. That's my mistake. There's 10 digits, not 1. Not 9, rather. Yeah, excuse me. Yeah, plus 9. Plus 10, rather. So it's 91. I see what I did wrong. Had the right idea. And now f of 3 size here. F of 3 is going to be g of 0 to 1,000. And we can say now we have each of these groups from 0 to 100, right? Or 0 to 99, we'll say. And because we're not including the last one, right? 0 to 99 times 9. And in each of these cases, we have 91 the first time. We would expect 91 again. However, in each of these cases, you have yet another number, another digit that's been added to each of these cases. And so you would expect them all to have the same number. And so it's some 90, we'll call it 91 minus some constant. Really, we would expect it to be the same for each of these, and then times 9. And so we would say, so far we have 1 plus 9 plus 9 times 10. So we have 1 plus 9, plus 9 times 10 to the first minus 1 it was. Right? Plus now it looks like 9 times 91 minus some constant k. Right? And this constant k seems to be, what could it be? We could do it for just the ones. So 1 with the first set of 101 to 102, etc., up to 109, right, 100 to 109. There's 1 that gets removed there. Or 100 gets removed. 100 to 109, 100 would get removed. So there'll be 10 numbers, 100 gets removed, 101 gets removed, everything else is fine. Once you get to 110, 110 gets removed, 111 gets removed, so 2 elements get removed from that one. And 112, actually that whole set gets removed. So you have 2, then you have 10 gets removed, and then I think you get 2 for everything else. So it'd be k is 2 times 9 plus 10, right? Because one whole chunk disappears. I'm looking for kind of a formulaic way to do this that extends to very large numbers, very large, very sort of a pattern, looking for like a pattern in the numbers. So now if you go to 120 to 129, 120 is fine, 121 is not, 122 is not, 123 is fine, all the way up. So there will be whole chunks get removed. But yeah, it looks like you're fine. You have 2 digits that are set, and those 2 digits are set for each piece, and it goes right. It'll basically do a round robin. So, you know, every set will have a chunk where the 2 digits are the same, and you can't use any of those. And then you'll have a chunk where they're not. And so this is 18. So 91 minus 18 gives you 81 minus 8, 73. Is that right? Let's see. You can actually kind of hack this question too, because this is such a small set. You can actually run these test cases, find out what the expected results are, and then just run a basically a switch statement here, and then you're done. You don't need to think at all about the question. However, we're not gonna. That's kind of cheat. It's kind of hacked. It's kind of somewhat cheating, somewhat kind of a hacked way of doing things. But you could do it that way too. It's pretty. It's sneaky. It's not good. I shouldn't praise it. Just say it's not really the right way to do it. Not really what you're supposed to kind of suffer a little bit. Do some thinking. So you get 73. It seems. Actually, I want to check this if this is right. If it's 91 plus 9 times 73, 748. Let me just see. Oh, we're so close. Yeah, no kidding. Wow. Really? Where do we go wrong? 2 is 91. This is 91. And then, oh. Yeah. 0 to 99 is 91. And then 100 to 999 is a little bit different, right? You get that extra digit in there that kind of throws everything off. I was saying you get 91, 0 to 99. No, because it's not 91. It's not 91. Because the first set, you lose the 0, 0. In fact, no, you have 2 digits at each step. And so it's 8. You have 8 at each step. Oh, no, this is wrong. You actually would have 100 minus k. And, right, you lose 2 digits for each, and then one of them you lose 10 altogether. Actually, it's a little more complicated than that. It's... Oh yeah, no, that happens 9 times though. Right, no, that's fine. That makes sense. Okay. Yeah. 100 minus 18. It's 82. 9 times 82 plus 91. Or minus 91. Actually, this is what they said. 738, 739, excuse me. How did that happen? I got this totally wrong. Something's wrong here. I'm not doing this right. This calculation. You have 91 for 0 to 99, and then for 100 to 199, right, you have that 9 times, from 200 to 299, 300 to 399, etc. And what's going to happen is, excuse me, if the left digit and the right digit are different, then it's only the middle digits. So if they're 2 different digits, there's only 10 digits to pick from, then only 8, you're only going to contribute 8 of those 10 times. Or rather, yeah, you lose 2 10 times. And then also, you lose 2 10 times. And then also there's one point where that actually happens 9 times where you lose 2. And one section, the 2 different numbers are exactly the same when you're dealing with, for instance, like 110, 111, 112, all the way up to 119. And that, you'll lose 10. And that's going to happen once. So this ends up being 28. Okay. 100 minus 28 times 99 plus 91. 739. Okay, there you go. What is this, 82? No, 72. Yeah, okay. So, $72 is 81 minus 9. Wondering if that's relevant here or not. Nine seems like just a special number in all of this. Just wondering if this is relevant, this means anything. Now, next number. N equals 4, right? I like how this took 4 milliseconds, even though it's just returning a number. Hi, how's it going, Garvey Mohammed? Hello, welcome back. Hello, hello. Welcome, welcome. Hope your day's going well. If you make this a constant expression, this would be very fast. But anyway, so now the next set. So you have, I call it 739 plus. Now if we go to 10,000, so we're going to do again 9 times 1,000. And there's a whole bunch of different ways that we lose numbers for 1,000. It's a very similar thing. Basically, you have, starting with 1,000, you have 3 different numbers, and they're kind of all changing. You have all these different combinations of three numbers with one number set. So you have from 1 to not 1. You have 9, yeah, 9 of these three different numbers. If any of those three are equal to that first number, then you won't have a solution. Now, normally those three different numbers you would have, I think, 72 of, right? Because those three different numbers would constitute. Actually, no, excuse me. You would normally have almost 739, not quite. In fact, it's slightly different because you're considering the leading zeros, sort of, or the trailing zeros, more like. It's not quite 739. It's very similar to the previous calculation. 100 minus k, or 100 minus 28. 100 minus 28 for each set of 100. And now oh yeah, let me read the problem. Fine, and you? What's the problem about? I'm watching with my phone. Oh, okay, very nice. Hey. So the problem is, given a non-negative integer n, count all numbers with unique digits x, where 0 is less than or equal to x is less than 10 raised to the 9th. So you would have something like, if n is 2, then you want to know how many numbers from 0 inclusive to 100 exclusive, so 0 to 99 inclusive. How many of them, those numbers, have unique digits? In other words, like 99 wouldn't count, 66 wouldn't count, 11 wouldn't count, right? Actually, you can kind of figure that out, that would be 100 minus all of the double digits, right? Of which there must be 9, because there are only 9 digits that could be doubled. You can't have 0, 0. So that's kind of a quick, easy one. And then they say this is bounded from n is going to be 0 to 8. So the biggest one would be 10 to the 8th, which is, I think, 100 million. Yeah, 100 million. So that's what they're asking for, is to count these things and try to do it efficiently if you can. So it's a very, very interesting question. Now, I want to say, for 10 to the 5th now we're looking at, you have 1,000 numbers, you have a 1 in the front. The first 100 numbers are very similar to the previous calculation, except now what's going to happen is you have an additional number which is going to remove a whole lot of these possibilities for each 100. So let's say it's 100. Let's say it's like the first 100, like for 1,000 and 1,000 to 1,099, right? Something like that. There are a certain number of ways that you can choose these numbers. Actually, you could think of this as all of the permutations of unique digits. So, selecting from a set of digits of size 4, let's say, would be sort of, you have like 9 choose 4, for instance. However, then you have, for each of those selections, you have the permutations. So if you did something like 9 choose 4, right, this is how many ways you could choose 4 digits. And we're going to do 9 because we're going to do 10. So this is a little confusing. We're going to do 10 choose 4. However, we also have to subtract a certain number of these. The reason why we can't do it quite the way I would like to do it right here is because you can't choose leading zeros. So it gets a little confusing because there's a certain number of things that we've got to remove that have leading zeros, certain cases. And I gotta think about that for a minute here. What's 10 choose 2? Let's try that one. Let's keep it simple. 10 choose 2 would be 100 times 9 over 2. This gives you 45. Which is actually way less than 91. And the reason why I think it's actually times 2 again, 2 factorial. So really these are actually just the permutations. It's 90. As it turns out, you can have the leading zeros in this case. The reason, then you would add 10 choose 1. So 10 choose 1 initially, or you have 10 choose, no, wait, 10 choose 1 is 10. We subtract 1 because, actually that's confusing too. They're all confusing. They're all confusing. It's not 10 choose 1, it's 10, it's just 10. 10 choose 1 times 1 factorial is just 10. I'm just thinking the first set, the second set, the third set. So like, if you have 10 to the 0, there's only 1, 0. If you have, 10 to the 0 is 1, so it's between 0 and 1 inclusive on 0 and exclusive on 1. If you have 10 to the first, then you have 0 to 9 including 0, not including 10. Yeah, just 0 to 9 inclusive. Which in that case, that is all the digits. That would give you 10. That's actually correctly 10. This one though, you run into some issues because 0, 0, 0 actually counts because the leading zeros, that we don't care about the leading zeros. So actually you could say you just need to enumerate the number of leading zeros that we threw out, and the number of cases where you had leading zeros that we tossed out. That's really all you need. Is just have to add those back. I gotta think about that for a minute. You can use SO, or you want to solve it with math. Yeah, you solve it with math. I don't know what SO is, but you could use a, what do they call that? You could also use a brute force approach, although brute force approach I think would be kind of difficult because the way it's been constructed, right? If you have numbers, if you have 10 to the 8th, right, 100 million numbers you have to go through. If you do something that's like You could maybe do a dynamic programming solution, actually, possibly. I'm actually not really sure. You probably could come up with a dynamic programming solution, but I think it's actually easier to use I think it's better to use like a maths solution. So I'll think about that for a bit. But yeah, one way of doing this would be to like generate the next set of numbers from the previous set of numbers, I guess. Something like that. Certain considerations. I'm not sure. Actually, I'm not even sure if you could do a dynamic programming solution. I'm not really sure. Because there's so many numbers involved that if you hold all of those numbers, you run into some problems. So I'm not really sure. But I do think taking all of the permutations that doesn't have duplicates is great, and then you just need to count all of the things that you threw out that had more than one zero, which I think is actually, if it's like, if there's sort of f of x, I think it's going to be, or f of x, yeah, f of x, it's going to be, you know, this, or we'll call it f of n, right? F of n, it seems to be f of n, 10 choose n, and then add, I think, f of n minus 2. Something like this seems to be probably sufficient, and I'll explain why I think that in a moment. It just seems to be like that, where f of 0 is 1, f of 1 is 10, and then f of 2 is, yeah, f of 2 is 10 choose, no, it's not 10 choose 2, I'm sorry, it's a falling factorial, which basically looks like this. N factorial. It's kind of like it's 10 times 9 times 8 times dot dot dot. And this is going to be n times n iterations. So it's a kind of a falling factorial. Certain permutations of a certain size. It's really a number of permutations. It's really, this is also referred to as 10 permute n. Another sort of combinatorial way of looking at it. And then, right, so you do 10 permute n would be 10 times 9 plus f of n minus 2 is 1, which gives you 91. And then f of 3, here's the moment of truth. I don't know if this is the case. Like, I'm not really sure, quite frankly. I don't actually know. But we'll see if this makes any sense. F of 3 is then 10, 9, 8, right, which gives you 720. Excuse me. Right? 10, 9, 8, 720 plus f of 1, which gives you 730, which is wrong. 739 is what you're supposed to get for 3. So this is not quite right. This is some extra term that you gotta add back in. In fact, that extra term happened to be, what's 739 minus 720? 19? It was 2 times f of 1 minus f of 0. That's kind of interesting. I'm not sure where that came from. But the 19 numbers that we didn't count would be 0, 0. Oh yeah, because we don't have any of the permutations of size 3 or 2 or 1, right? I want to say you actually add Yeah, what about the permutations of size 3 and 2 and 1? Well, all of those, 3, 2, and 1, all of the 2 and 1, I want to say actually, yeah, all of the 2s and 1s basically are the leading zeros are the size of 1, 2, and 3. And we do consider them, but most of them we just throw out. So the ones that get thrown out are the thing that's weird about that is oh, I'm sorry, these are 3 numbers we're taking, I'm sorry. So yeah, the leading zeros of 2 and leading zeros of 1, or 2 zeros and 1 0. So 2 zeros, there's actually even 3 zeros, right? 3 zeros, 2 zeros, 1 0, and 0 zeros. Those are the 4 different sets we want to consider here. And 0 zeros is going to be 9 choose 3, right? Don't pick 0 at all. Very straightforward. Or not 9 choose 3, but 9 permute 3. And that permutation guarantees uniqueness, right? Because all of these digits are different. So 9, yeah, because 9 permute 3 is 3 digits without zeros. 9 permute 2. But now here's the thing. There are zeros even in the 3 digits. It's just the leading zeros in the front, those are the ones we're trying to get rid of. So we can do, if we want to get rid of zeros in the front, we can do 1 through 9 times any choice of 2 digits. So it could be, that first group could be 9 times 10 permute 2. But the problem with this is that now you could have duplicates. So it really doesn't work, does it? How about we do 0 zeros, 1 0, 2 0, 3 0, right? If there's 2 or 3 zeros, no, well that's the problem, right? Again, if the 2 or 3 zeros are leading numbers, then you're stuck, right? Then you have a problem. So that's kind of good because you don't choose. Those would get chosen anyway for your permutations when you're considering permutations. However, how about this? How about no? Keep running the same problem over and over again. You want to include the zeros. However, there are some numbers where there are zeros in front, which are fine. Those would be 2-digit numbers, basically. And then there are numbers where there would need to be multiple zeros because they're basically leading. Just trying to identify which numbers are we missing, right? If we did 10 permute 2, right? That would give us 10 times that would give us 90 numbers. what are the 10 numbers we're missing here, right? These are all unique, all different numbers with unique digits. 0, 0, that's missing. That's it, actually. It's just that one. Everything else is there. All the numbers that we're looking for. But the numbers that we don't have are right. All the numbers that are. There's sort of 9 numbers. 11, 11, 2, 2, etc. All the way up to. All the way up to 99. Super interesting question, man. Really interesting. So, maybe we can like break this into pieces. So for a given n, you can choose. You have 10 numbers to pick from, 0 to 9. Whatever number you pick, 0 to 9, all of the possibilities after that have to be. Just throw that guy in the middle of nowhere. All those possibilities after that have to be duplicates without duplicates themselves, and also not include 0. So now there's only 8 possible choices. Now that's not true. If you pick 0, there's 9 possible choices. You could still pick 0 again. You could pick 0 to begin with as many times as you want. However, you still reduce n to n minus 1. For all the other cases, you only have 8 possible characters left. You decrement one less character to pick from each time, whereas you don't if you pick zeros. And so let's do for like 3. So 0, 1, 2, 3, ... to 9. This you could pick. This could be followed by any of 0, 1, 2, all the way to 9. And all of these can only be followed by, 0 to 9, not including 1, and 0 to 9, not including 2, etc. There's 8 choices, but what's interesting is that of these choices, again, each 0, you still have any number of choices you want. Trying to build like another kind of the way that you would derive the factorial, the number of permutations. I'm trying to come up with another way of doing that, a kind of counting algorithm or something, some kind of way to count this from sort of first principles, I guess. Excuse me. So for 9 out of 10 times, you have basically f of n minus 1 with 1 less digit, 8 digits to pick from, or 9 digits to pick from. Now that's not true, right? Because you still could pick 0. That's not entirely true. But you do have 1 less digit. That's true. F of n minus 1, 9, including 0, right? You can always pick 0. Plus 1. What is going on out there? Is it a dog? I don't know what that was. 1 less character now. But this is, you still have 10 different choices to pick from. So maybe that's what we should do. We should have, you know, how many choices you have left at each step. And actually you could do, instead of 9 out of 10, you could do 9 times plus this, right? And then maybe you can use dynamic programming to do this then, right? And that's the first iteration. And the next iteration would be, again, 9 times, oops, f of n minus 2. 9 of these cases, each of these, for I guess f of n minus 1. And it would be 8. If we said 9, right? 8 and f of n minus 2. And this would still be 9. You wouldn't have used, for one of those cases, you won't use the 0 for each of these spots. You have this kind of recurring thing, recurring structure. So really you do have something of a formula. You have f of n, let's call it r, is going to be 9 times, and really it's the character set. I mean, it's a finite character set, but it's going to be the size of the character set minus 1. Call that k minus 1. Which is 10 times f of n minus 1 r minus 1 plus f of n minus 1 r. If that makes sense. So there you go. That should be a solution where we can actually delete all of this, I think. Oops, I need to do that. I don't really intend to save these, for the most part, these notes, where f of 0, I guess 0, 0, is, or 0, 1, if there's one character to pick from, and n is, I want to say 1, 1 is 1. I want to say something like that. So then f of 2, 2 is then 9 times f of 1 r minus 1, which is 1, plus f of 2, 2 and r is 1. And then so this is 1. But what is this? F of 2, 1. That's 9 times f of 1, 0 plus f of 1, 1, which is 1. Oh yeah, which is 1. Which should give you 10, which is 10. And I want to say f of x 0 is just 0. Right, that seems to be sufficient. So we can say f of 1, 1 is 1, f of x 0 is 0, and we should be able to get everything else from there. So you can use dynamic programming then, I think, to go backwards. So like this, you could use a recurrence relation to do this. Oops. So let's do that. Let's try them recursively, and then we'll go use dynamic programming. So auto recurse. We'll get to that in a second, what those are going to be. And we're going to return 9 times f of, we said it's n minus, we'll do a and b, right? Int a, int b, a minus 1 and b minus 1 9 times, plus f of a minus 1 and b stays the same. And then we're going to recurse on n number of numbers, 10 total to begin with, and recurse. And in fact, we can just return that. And let's see how this goes. Oh, we don't know. Yeah, okay. Oh, and I'm missing. We don't really need this. It'll figure it out with base cases. I think that's all we need. That's kind of one of the first things I want to Stack Overflow. Okay. So, oh. No. A is always decreasing at every point. B doesn't always decrease though. So we do need something for when A, but when A is 1, we could say if A is less than 1, right? Let's say thinking like f of 3, 3. If we get, we're not going to do 9 times, we'll do f of 3 of 2, 2, and then f of, we said 2, 3, right? And so we have f of 2, 3 will give you f of 1, 2, and f of 1, 3, and then f of 1, 3 will give you f of 0, 2, which I think this would go for a while, right? And f of 0, 3. Oh yeah, that's why this goes on forever, right? I think if a is 0, then it's just 0. I think if either of these are 0. 0. Interesting. What do we get with 1? 1 and 10. Why do I think I made a mistake actually? It should be 1 and anything. Not 1 and 1. That was a mistake. Doesn't matter what B is if A is 1. And then if either of these are 0, return 0, right? 1 gives you 1. What about 2? 2 should give you 10. 1, 10, and 100. Just gives you everything, huh? Interesting. That's interesting. So, if you only have 1 digit, no, excuse me, if you have 1 digit, you return not 1, but it's B, believe it or not, right? It's one of these digits. Excuse me. If you have 0 digits, that's confusing. F of 0 is what? Well, no digits, right? No digits to pick from, and no digits to pick from, except 0. You always have 0. Is there? Which is a 1. So you always have a 1. And if you have one digit, it's, I want to say if you do f of 1, 10, That should give you 9 times f of 0, 9 plus f of 0, 10. And this gives you, I think these are both 0. We're supposed to get f of 1, 10, f of 0. Now forgive me for this because I'm stumbling here. Oh, it's very confusing because it's a power of 10. That's why. Ah. Oh no. Okay. Oh no, okay. When n is 0, we return 1. That has nothing to do with our algorithm. When n is 1, that's when things get interesting. That's when you have f of 1, 10, which should give you 9, or really should just give you 10, just out the gate, 10, right? Yeah, okay, let's do it that way. Yeah, A is 1, return B, right? Either of these are, yeah, and if n equals 1, no 0, return 1. Okay. Alright. Whoa. That's pretty good. We got the 91. We didn't get the 820 though, that's wrong. We're a lot closer now though. What are we supposed to get for 820? For 3? So if we do f of 2 and 10, that'll give you 9 times f of 1 and 10, and 9 rather. Right, 9 of those times you remove a 9 of those times you remove a character, but 1 of those 10 times you don't remove a character from the set. And then you say this is 9 times 9 is 81, and then f of 1 is 10. That gives you 91. Now f of 310 though, get something entirely different. You would say f of 210, which fortunately is where it's recursive. And no, sorry, it's not. F of 29 times 9 plus f of 210. F of 210 we already showed to be 91, so that's nice. However, for f of 29, it's a little different. F of 29 becomes f of 9 times f of 1, 8, and then also f of 1, 9, which gives us 9 times 8 plus 9. So if you had 9 characters to pick from, but you could only pick, if you had 9 characters to pick from, but you could only pick yeah, you could still pick 0, and you could pick 8 characters. Oh, so this is wrong. This isn't 9 anymore, right? That's a mistake. This changes as you go. Yeah, this is incorrect. This is actually 9 minus 1 is 8. I got that wrong. Eight of those 9 characters are unique, but the zeros you could pick as many as you want, so it's actually supposed to be 8 here. That's what's wrong. That's why we overshot, I believe. So 91 over there. We have 9 times, this is 8 times 8 plus 9. $73. You have 9 times 73. Oh man, it's not the most disciplined in terms of writing these things. $7.48, we're so close. We're so close, yet we're so wrong. How do we get this so wrong? Is this 9 after all? I get this feeling like this isn't right. Do we even subtract, do we even add 9? I don't know. It's not 8, it's actually, it's B minus 1. How about that? What does that give us? We're off by 9. What did we do wrong? What did we do? What did we do? I want to say that there's something up here. How? I gotta go through the derivation again. So we have n characters to choose from. That's 0 to 9. There's 10 choices. Then if we pick 0, we have still n minus 1 characters to choose from, two choices to make, and we have still 10 different options here. That didn't change, but these other 9 times, these other 10 minus 1 choices, or yeah, these 10 minus 1 times, 9 times, we have 1 less character to pick from. We have 0, 2 to 9, we have 0, 1 to 9, and so on. So 9 times we have 1 less choice, and these have 9 choices to pick from, right? Then for each of these, then these split off, right? From here, if you pick 0, you have n minus 2 and 10 choices for those. Then for these, you have again 9, right? 9 times n minus 2 choices, and it's 1 less character, right? Each of these have 9. So this is like 1 times 10 with n minus 2 choices, one time here, and then each of these are 9 times by 9 characters to choose from. So I'm not so sure, you know, I'm not sure how this recursion is supposed to work exactly. I'm not sure that the recursion I have written here actually makes sense. It can't be right, right? We undercounted or we overcounted? We overcounted. We had too many things. We needed to subtract more things or not add so many things. Excuse me, we added too much. And also over here, same deal for each of these zeros. So we have 8 times we have 8 characters. and that's each of these instances. And one of these times we have still 9 characters. And this is somewhat recursive, right? N minus 1 and 10. And this is sort of, now how is this wrong though? This f of n r being r minus 1, f of n minus 1, r minus 1, plus, there's always that one character that's f of one less decision to make, but r doesn't change. And we're saying this is not correct. And if you look at n equals 3, that's where it falls apart. When a is 1, whatever how many choices of b you have is just it. When a is less than or equal to 0, you don't have any more choices. When b is less than or equal to 0, you also have, b is never less than or equal to 0 though. B is always 1. I don't think you ever really need this then, if you're, how does this go? 0, 10, 91, as soon as you get to 3, it's wrong. Oh man, kind of stuck on this. So, for 3, you would have, 9 times f of 2, 9 choices, and then f of 2, 10 choices, and then for your second choices, you have the choices you can make here. You can make, so 0 is selected in these cases, right? You do 0, 0, and that gives you a bunch of choices. 0, 1, a bunch of choices. All the way down to 0, 9, and that's a bunch of different choices. And that'll leave you with f of 1 in each of these cases. This is f of 1 with 10 characters to pick from. This is f of 1 with also 10 characters to pick from. Right? Not exactly, actually. These have one less character. Right? Yeah, these have one less character. And there are 9 of these. Right? This one you could just pick all 10. These ones you can only pick 9. This should give you 91, which I think it does correctly. I think we get 91 correctly here. This other part, that seems to be a problem. Right? F of 2 is fine. It's permutation times n times 9. It's a permutation times 9. I don't think so. I think it's a little more complicated than that. I don't think so. So this is fine. This part. It's this part that there's really issues. So each of these ends up being, you have 2 choices left. You can pick 1, in which case now you have 9 choices. Right? No, see, this could have a 0. But no, but it's 9. Yeah, it could be, yeah, they all could have 0. No, that's fine. We never get rid of zeros. If we don't pick 0, right, we just can't pick dot dot dot. We can't pick 1. Oops. And then similarly, there's a bunch of these. There's 9 of them. Go to 2 0 and 2 1, and then 9 0 and 9 1, right? And dot 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 dot. And each of these possibilities will say there's yet another digit that we're removing. We have, this is f of 1, 8, right? Of the choices that we have here, we could pick any of these except, oh, no, that's not totally correct, right? Because this is, so there's 9 times f of 2, 9. The problem here is that you could pick, for this guy, 1 of 8, right? You could pick 0 through 9, excluding 1 and 2, right? Which is -1. And by the way, each of these have 8 of them, right? 9, 8. There's 9 of these, there's 8 of these guys. F of 1, 8. And then there's 1 of these guys, which this is f of 1, 9. Now this is not actually f of 1, 9. Because you actually can't pick 0 after this point. So this is wrong. That's why we overcounted. We overcounted by 9. 9 times, we added an extra 1. Wrong. Wrong. Wrong, 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 wrong. And that's what we got. That's exactly what we see. I mean, for an interval, like between 0 and 10, there are 10. I'm not sure what you mean exactly. I'm not sure what you mean. So I'll come back to it. I'll come back to it. Maybe I may just be not thinking hard enough about what you're trying to say, or yeah, not spending enough time trying to figure it out. And forgive me for that. Forgive me for that. I shouldn't say forgive me. I'm not asking forgiveness for that. Actually, I shouldn't do that, because I probably won't spend enough time. Like if I'm working on a problem, there's a very good chance that I'll try to understand what's being said in chat, but I'm not going to guarantee that I'll always understand or always give enough time to understand. It's kind of a lot. It can be a lot. It can be a lot. So this is why. So actually, this is wrong. This ends up being, you can't pick 0 again after this. Once you've picked something that's not a 0, from there on in, you are no longer choosing things for these 9 elements. It's actually not going to be f of 2, 9. It's actually going to be, this is 9 times f of 1, 8. And this happens 8 times. we're going to call this g of 2, 9. Use a different function. So we'll have f and g. Use different functions. G of 2, 9 gives you a leading number that's not a 0, and so now you can no longer have as many zeros as you want in the front. And so now I think you get a permutation. Now you get, excuse me, of the 9 numbers, so you selected a number 1 through 9, right? Of these 9 numbers, they have g of 2, 9, 2 choices, and one less digit to pick from. I think it's you have one less digit to pick from, and also one less digit to pick from, and then the number of times that this occurs is, right, this f of 1, 8 happens 9 times. Times g of 1, 8, which is b times g of 1, 8, which is really a permutation, right? Is that right? No, I don't know. What is this? This is, so you would get 91, you get 9 times 8 plus 91. Which is exactly right. But I don't know what to make of this or think of this exactly. Huh. Between 10 and 100 is 9 times 9. 81 between 9 times 9, you say? Between 100, 1,000 is 9 times 9 times 8. Huh. Oh, I will try. Oh, you might be right. Yeah, maybe. I don't know. Possibly. Possibly. 9 times a permutation in between. That could be true. Maybe that's what I'm missing here. Maybe that's what I'm missing. I think I know what you're saying, but I'm not sure if it's true or not. I don't know. So actually, we have 2 different functions here. Let's do f of 4, 10. It looks like it's going to be 9 times g of 3, 9, right? Plus f of 3, 10. I think so. Which is f of 310 we said is 739. And g we said, yeah, basically g is a permutation pretty much. It's 9 permute 3, which is 9 times 9 times 8 times 7. Right, which I think I would have determined that. I know you kind of helped me a little bit, but I think I would have figured that out, right? Because it's just b, and then it's really b and g of, basically if g of n r is r times g of n minus 1, r minus 1, which is basically r times r minus 1 times r minus 2, whereas this the total number of things are n, which is really just n, or really rpn. Oh, is that right? Did I do that right? Wait a second. Oh no. Actually, this is reversed. Yeah, well, that's fine. Yeah, it's R permute N. Right? So this ends up being plus, right, f of 310, which is 739. I think that's it. So this actually really is, you could say f of n, you could drop the 10, you could say it's 9 times 9 permute n minus 1 plus f of n minus 1. I think that's what you end up with, as pretty much as you described. Yeah, I agree with you on that. So the permutation is, computing a permutation is kind of tricky. Permutations is tricky, where f of 0 is 1, or f of 1 is 1, or f of 0 is 1, f of 1 is 10. F of 1 would be 1, 0, 1 plus 9 permute 0 times. I think it's just 1, that would give you 10. Yeah, I think f of 0 is 1, it's fine. We'll just run a smaller permutation. I'll also make this unsigned, so I don't have to check. And we're going to say auto permutations int n int r ret equals 1 for r greater than 0 decrement r ret times equals n minus r, or just n, something like this. So when r is 2 and n is 2, you get 2, right? Then it goes to 1, 1 is greater, and then, yeah, that should be fine. So we'll do a equals recurse, yeah, and n doesn't really matter, or 10 doesn't really matter. You could do, we'll do x then, or xn, whatever you want to do. So it's x minus 1, and it's going to be 9 times permutations of n and r is, it's 9, and r is the next thing, which is, what did we say r was? It's x minus 1. That's what we said. Yeah. And a and x is equal to 0, return 1. And that's basically what we want. There we go. Yeah, I agree with you. Very good observation. Good observation. Let's see if we got it. How did we do? Yep. Here we go. I think those are all the test cases, right? Hey. I got accepted. Yeah, very good. You did good. Yeah, well done. Well done. That was pretty clever. What do you call that? That was pretty clever observation, right? You made the right observation. So, I don't know I don't know. I don't know. I guess it's just something you notice. It's just something you notice. I probably could have guessed that from the first. Yeah, it's like just something you notice in the data, how it's organized. Probably could have guessed that after I had 9 times 9 times 8. I could have tried 9 times 9 times 8 times 7 plus the previous, and I could have just known. I don't know how I would have figured that out though exactly. I think the problem was that I kind of missed this portion here, that this is different from this other spot. But yeah, really interesting question. I like this question a lot. It's a good one. It's a good one. Also, I'm glad Garby was here to beat me to it. Yeah, I appreciate that. I like, what is it? I like questions that I can kind of do with the stream, I guess, and questions that I don't necessarily, I don't necessarily know, something like that. I don't know, something about it. It's good. But yeah, the people who did it without very much memory, by the way, are people who basically computed all the numbers and then just returned each one in like a switch statement. You could do 100% memory on this too. So yeah, pretty interesting question. I really like this one. It's one of those questions that gets a lot of downvotes because people are just annoyed because they're like, who's going to ask this in an interview? But it's like a very maths kind of a question, and has a lot of like, kind of, can you detect the structure of the data kind of a thing? And if you can, then you can come up with a solution. But if you can't, and there's like reasoning here. I mean, the reasoning is pretty simple. It's if you lead with a 0, you have a special case where you basically are recursing. But if you don't lead with a 0, then you have 9 times something else, which that actually could just be the permutations, which was the problem that I had. I was trying to figure out, I was like, wait a minute, why can't I just pick all the permutations? It's because the leading 0. So actually it's really simple if you understand it. So you would say, for the first leading 0, you recurse, and you have, whatever the solution is, and then you add to that all the other leading numbers, which are not leading zeros. There's 9 of them, and you multiply that. The function for all of those are actually just the permutations of the remaining characters, which there are 9. So it's actually a very clean problem if you clean recursion, if you think of it that way. And you could do dynamic programming also to do this. I kind of want to do it that way. Actually, you could accumulate. You could do an accumulation. You could do a double dynamic programming solution to get the number of permutations too. So watch this. You ready for this? How about this? Int p. I didn't end the stream yet, right? Yeah. Oh yeah. This should be interesting. I got an idea. The whole problem is with the zeros to remove it. Yeah. Exactly. Right. Exactly. Correct. So 9 and total, right, is going to be 0. And we're going to say, no, we start off int n, yeah, so we'll do 4 n minus minus, or minus minus n, greater than 0. Or n, you could do, yeah, n greater than 0, n minus minus. And we're going to do the following. P multiply equals, oh, no, yeah, total and total P equals 9. And we'll put this at 8. No, let's do 9, yeah, 9, 1, 1, okay. Total P is going to keep track of the size of the permutations. It's going to be multiply itself by P, and then we're going to also decrement P afterwards. The total is going to be equal to the previous total plus equals, right, which is f of n minus 1, 9 times total p, the new permutation, right? So initially we're going to do, so when n is 0, we return the total at the end. N is 0, return 1, right? I think n is 0 is 1, right? No, n is 0, yeah, n is 0, we get 1. When n is 1, we say this is 1 times 9 is 9, and then we add, oh, this is wrong, huh? Oh, we add to itself 9 times total p. I think I actually do this second, do it second. So let's see if we do this, what happens. Yeah, so because both of these are, basically both of these could be dynamic programming solutions. Yeah, like, I like that. I like that. Hey! Both of these could be dynamic programming solutions, and they both can actually be sort of optimized where you only need the previous value. You don't actually need all of the previous values. So you can calculate them both in tandem. Both of these functions, the permutations function as well as the function that they're looking for. So you can compute this very quickly, which is pretty neat. So yeah, I mean, obviously we were already at 0 milliseconds, but this is, I guess, it uses less memory. I don't know. This is, like, in my opinion, a little more clever, a little faster way to implement this. So I like that. That's pretty cool. That's pretty cool. Not bad. Not too shabby. Not too shabby. All right, let me go. So yeah, we spent an hour and a half on this one. Wow, spent a lot of time thinking about it. So thank you all for watching. I will talk to you all soon. Thanks again for coming by and saying hello. And I am going to end the stream and start another problem and stream again, and probably try to spend an hour on the next problem. So we'll see how we do, though. Obviously, if it takes too long, then I'll break it up into pieces. So yeah, thanks for watching, and take care.